So we start now. Okay, so we are live now. Hello, everyone. Welcome to today's session on buckling simulation for Chroma 3D printing. So for 3D printing in fresh concrete. Today we have Shaun Wu, who's going to talk to us and present sort of the research that they have been working on over the last couple of years, basically on 3D printing. Shaun is here joining us from Singapore. And just so that you know, for example, who is in this webinar session. So we have Shaun, who is going to be presenting for us. Then I am Matthew Tam from Chroma 3D. And then joining us from Chroma 3D is also Clemens and Zeynep.
Hello.
Hello, everyone.
And we will turn on the video in a second. If for anyone who wants to ask any questions or if there's any problems with the broadcast, please write in the Q&A and we will try our best to answer these questions. Shaun will basically present for about 45 minutes or so, and at the end there will be some time for questions. And so please feel free to pose your questions. Shaun, can you please share your screen now?
Yeah, can you see my screen? Maybe I can do again. Share the second one. How about now?
Mm-hmm.
Yes.
Okay.
And I'll put you on video too.
I think everything's working now, right?
Yes, everything's live now.
Okay, cool. Thank you, Matthew, for the warm introduction. And my name is Shaun Wu of Witteveen+Bos. I hope everyone is doing well during this virus crisis. It's a bit weird that presenting without seeing everyone, but I guess this is something I need to adapt. And today I want to share with you some of our concrete printing development. I will spend around 20 minutes to talk about this concrete printing development and another 20 minutes in buckling simulation. And before I jump into today's topic, I want to briefly introduce our company first. So Witteveen+Bos is an international engineering and consultancy firm since 1946. We have over 1,300 colleagues around the world, and our offices are located in 11 different countries, headquartered in Netherlands, and at the moment I'm working at a Singapore office. So within our company, we mainly focus on 4 different areas. First in built environments, second in energy, water, and environment, third in delta, coast, and river, and last one in infrastructure and mobility. And within the built environment area, we have a group called Digital Construction Group. So I think it's always nice to talk about why we do digital construction and why we do concrete printing. So first is from the environmental level. Our cement production contribute large amount of CO2 emission annually, but it doesn't really change that concrete is a good structural material. It's durable, it's fire resistant, it's also quite cheap, quite affordable. And what we need to do is using less concrete, apply material where needed. Second reason is health and safety. We want to reduce the fatality rate in our construction site, and tying reinforcement bars is such hard work, and typically it causes some health issue. And our construction site is not always safe. Third reason is the productivity. As you can see, the red curve in the bottom is our construction industry. And our construction industry is a huge industry. But our productivity is pretty much the same to 20 years ago. So yeah, compare other industry like manufacturing, we need to advance the way we build today. So we see the room for improvement. Last reason is because of aesthetic. The demand for affordable housing is a hot topic, but the way we build today is just not the aesthetic in my opinion. So all these challenges give us a motivation to digitize and automate the construction industry. Then this leads to today's main topic, concrete printing. Back to 2014, Witteveen+Bos was one of the partners in 3D concrete printing research program in TU Eindhoven in the Netherlands. So for this, this is our first robot. It's a very simple four-axis gantry robot. And over here in the right, you can see we have a small pump. We add dry cement material in here. Water is added automatically in the pump. And this pump will deliver fresh concrete materials through hose and deposit material on nozzle. And this gantry robot getting its motion from robot controller on the left side here. And this robot controller also communicate with pump. So everything is interconnected. So yeah, this is how does it look like, concrete printing in action. So as you can see, this is a layer by layer extrusion process, printing fresh concrete on top of each layer. You may also notice there is no foam wall at all. Everything we print is fresh concrete. So we eliminate the need for customizing one-use formwork, especially for those non-standard or complex geometry. At the right video, if you shift the print path every layer, then you can produce this subtle pattern on the concrete surface. So this is another added value. You can customize pattern, customize design, customize the overall geometry. So let's look at the challenge of concrete printing. As I described before, everything we print is fresh concrete. So fresh concrete is like mud. It's very soft, but it's also very heavy. So this is what happens if you print too fast. It was supposed to be just a straight column or straight cylinder, but it tumbled down because the fresh concrete is not stiff enough to support the self-weight. But if you print too slow, then you will get a poor bond between each layer, meaning the integrity of concrete structure is compromised. So in order to understand not print too fast and not print too slow, then we need to do some research. So we not only need to understand the material properties of hardened concrete, we also need to understand the property of fresh concrete. So we consider fresh concrete as a soil, and we make use of existing geotechnical testing method to test it out. So the image in the left is our testing device for compression. So the idea is you pour the sand into the chamber, you place your testing sample beneath over here, and this device basically it can measure the load and displacement. The right side is the device to measure the shear. So what is the result for this testing device? These are two graphs. They are describing the time-dependent strength development of fresh concrete in compressive strength and in stiffness module. And once I have these two graphs as information, then I can build a numerical model. So this is what we call buckling simulation that's using Karimba. And basically, it's a finite element analysis to build a structure to digitally predict what will happen prior to the physical printing. And according to the setting of the geometry, the printing speed, the material properties, and so on. And I will discuss more in the end of the presentation and go through the Grasshopper definition. Next thing is reinforcement. So concrete without reinforcement is not useless, but we know it's quite limited. So generally, we have three ways to incorporate reinforcement with concrete printing. We can add reinforcement before printing, during printing, and after printing. And what you see in the picture here is an example of adding reinforcement during concrete printing in the manual way. And of course, you will think, hey, if it's possible, we can add reinforcement in the automatic way. Then you see here, basically, we have a spool of a metal wire that is placed automatically with the printing filament, following to the correct robot printing speed. And sometimes maybe one single wire that is not enough to satisfy structural performance. So in the right image, it's also possible to add more metal wires during the printing. So we know that, hey, we can add reinforcement manually and also automatically. Now we understand the material properties. We understand how to add reinforcement in the concrete printing. The next challenge is doing a small real project. So in 2017, we printed a small bicycle bridge span around 6 meters. So the first step is actually to print a scale model. In this case, it's a 1:2 scale model. And we test its structural performance in the university lab. And the result for this model is actually is structurally behaving just like a normal concrete bridge. So we didn't use any new regulation or new building code for this bridge because this is nothing more than a normal concrete bridge. And after the scale model, we started printing in full scale. The internal structure is like honeycomb, and the density of honeycomb can be adjusted according to the structure, according to the structure requirement. And if you need it to be stronger, then you simply you just make the honeycomb structure more denser. And this is what we mean that you can apply material where you need it to achieve mass customization. So we print segment by segment and assemble all the elements on site. Then we pre-stress the element by post-tensioning. Then placement. And finally, we did the final testing. The reason for the final testing is we might make some kind of mistake during the printing, during transportation, lifting, or assembly. So this final testing, it makes sure everything is in control and safe. So this is our first printed concrete bridge. And we know it's not that pretty. We know it's a big overkill. Safety factor is very high, but we managed to print a concrete structure for a real project in practice and also within the safety regulation. So next thing we look at it is investigating topology optimization. Compared to normal concrete structure, 3D printed concrete structure cannot be seen as an isotropic material. So to apply topology optimization is a bit difficult because printed concrete should be treated differently in tension and compression. And based on the investigation and the experience we learned from the previous bridge, we are working on a second bridge. So this time, the span is in 30 meters, so it's wider. The shape is optimized, so it's more organic. And we also minimize the amount of material we apply for this bridge. So you really can see the benefit of combination between concrete printing and topology optimization or an appealing form. So again, we print segment by segment, and all the 30 meters element are printing already. And this is to show you how does it look like for one part of the bridge. And at the moment we are testing it in the factory and waiting for the assembly on site. Next thing we do is housing, and we call project milestone in the Netherlands. And the housing is actually is way more difficult compared to the bridge. The printing itself is not difficult. the difficulty is you need all the different parties involved. So you need to have the academia, you need to have the industry, you need to have the government. So coordination, the project management become quite challenging for this project. So we design this residential housing based on the principle on concrete printing, and also we add reinforcement, insulation material. The picture is one of our mock-up. So we use this mock-up to test all the detail like waterproofing, installation for window, NEP, joint connection, and so on. So let's move to our recent project in Singapore. So here in Singapore, we are also working with concrete printing for construction in built environment sector. And Singapore has been focusing on what we call PPVC, PPVC construction. We call it pre-finished, prefabricated volumetric component. And the idea is just like prefab or precast. You build a small unit in the factory with all the NEP embedded. Then you assemble this unit on site to minimize the work in construction site. So first thing we do is, of course, we need to transfer our knowledge from Netherlands to Singapore. So we install the machine, and we have a different environment setting. We have different temperature than Netherlands, also different humidity. And we understand actually it's easier to print in Singapore because there's basically no season in Singapore. It's always hot. The humidity is constantly high. So these are actually added value for concrete printing development. Then we test again how to embed reinforcement in concrete printing. At the right side is another approach in this, and we print a permanent formwork, a concrete formwork, and add reinforcement cage in the hollow area. Then we cast normal concrete to fill it up. Once we understand there's no problem adding reinforcement, we started printing our small PPVC unit, and with a bit of a nice curve at the front facade. You can see over here, this is a curved facade. So actually, it's a double curved surface. And at the left picture, you can see one of the columns that was being printed. Finally, we print the beam element to connect 4 columns together. So this time, the reinforcement cage was added before printing, and we simply print around it. Then our first PPVC was complete, with all the necessary reinforcement embedded. In the right picture, you can see it's the internal part. Then in the internal part, we do some surface finishing. So it's very smooth from the interior part. But the outside exterior part, you still can see all the layer by layer appearance. So actually you can choose, you want to have the smooth surface, or you want to have the layer surface show you on your concrete surface. It's optional. So now I will talk about our software development. For our concrete printing software, we internally created a fully customized plugin within the design environment running Grasshopper, just like the Karimba. Karimba is a plugin for Grasshopper, and this Witteveen+Bos software development is also the plugin for Grasshopper. So this Witteveen+Bos software, it covers 4 areas: in computation, in geometry, material, and robot. And from these 4 areas, we have 4 main functions to cover entire concrete printing process. So they are slicer, robot controller, topology optimization. Last one is the buckling simulation. I will quickly go through one by one what they are and what they do. First one, slicer function. So idea is we need to convert our 3D model to printable objects our concrete printing is layer-based extrusion process. So we need to slice it. We need to slice our 3D geometry to layer-based principle for robot to operate. So based on that, we standardize 3 different printing strategy. First is what we call vertical printing. The print head and nozzle is always perpendicular to the ground, printing object. Second is tangential printing, meaning the print head and nozzle is always following the curvature of your object. Third is on-surface printing, allowing us to print on a double curve surface. And this is the simulation of how on-surface printing looks like. The print head is always following the surface normal, and the nozzle is always follow the tangent of the print path. So next function, robot controller. This controller is to operate different robot system. So this is one of our robots in Netherlands. We have the small six-axis ABB robotic arm. So we make use of this robot to do some small experiments and introduce our colleagues of how and what robotic fabrication can do in principle. And so in principle, we can also pour beer for you. So you can keep you stay hydrated during the work, no problem. And we also deliver this software to our client to help them conduct concrete printing. And for example, this robot is elevated on a static podium. Another one, of course, you can install your robot on a linear track as axis 7. So you can expand your printable dimension. And beside the robotic arm, we also work with a gantry robot for larger printable dimension. Third one, topology optimization, is more focusing on the design study. And this is a method to minimize the amount of material we need for concrete structures. So we apply this method to our bridge design and also slab design to see how stress line distributed in tension and compression based on the loading and your support area, so your support condition. And then how does it look like in the actual geometry? Investigating like from the shading pattern and also from aesthetic point of the view. And last one is the column study. Actually, we are looking for a client who are interested in this design, so we can provide the service for design, engineering, and printing this beautiful concrete structure for you. So yeah, if you are interested in this element, please contact me. So finally is our buckling simulation. As described before, everything we print is fresh concrete. So we developed this buckling simulation using Karumba 3D to digitally predict what will happen before physical printing, so to avoid trial and error. Then, yeah, actually this is my end of my presentation. Now I will go to my Rhino and Grasshopper to go through the Grasshopper definition.
Shaun, thank you very much for the presentation. It was very, very insightful to see some of your research. There was just one quick question about the presentation. Someone asked, how do you connect the reinforcement cage to the foundation?
So, okay, maybe I can go back to the Singapore project. Example, this one, right? So actually we have different structural elements. We have slab, we have column, we have wall, and finally we have beam, right? So the idea we have, how to say, so for the slab element, actually we print the profile of this slab, and then we place a mesh, then we cast normal concrete in this slab. And before we cast the normal concrete in, we actually have some starter bar pointing out of the slab. So when you print your wall element, you already have some reinforcement pointing out of this structure. So yeah, this is the way we to combine different structure elements together. I hope this answers your question.
And there was another question. Which plugin are you using for topology optimization? Topos or Millipede or other programs, for example?
Yeah, actually,
is this something?
Yeah, we tried different plugin like Millipede or Topo. We all try, but they all have some kind of the problem. So actually, in the end, we also develop internally, and sometimes we use plugins, sometimes we use an internal developed plugin. So it's really depend case by case. For example, if you want to use a 2D version, maybe you can use
the microphone gets out.
Yeah.
Yeah, thank you for that. Clemens also has one question.
Yeah.
I have one question regarding the concrete pressure, the pressure of the fresh concrete. Up to which height can the printed formwork sustain the fresh concrete pressure?
There's no formwork at all in the concrete printing.
No, but if you use the printed concrete as a formwork,
yeah,
and then pour in the fresh concrete,
yeah,
some horizontal pressure will develop from the fresh concrete, which can be quite high.
Yeah.
So, what's your experience here? What is the limit height that you can do?
Yeah. So for this one, the wall element actually we print separately, right? So the first wall element is the first segment. This is around maybe 1.2 meter high, and we calculate the pressure when we cast the concrete, and it has something to do with how wide you print your concrete, and also what is the volume, how much volume you cast the concrete in the foil, in the hollow area. So all of that actually is based on the calculation. If the calculation say okay, then we just cast it, and of course we do some safety calculation and also some safety equipment to clamp this element together to avoid like get expanded or just like to avoid that there are too much pressure inside this element.
Thank you.
Yeah.
And I
Yes,
want
I
to
think.
ask a question if we are
Okay.
already asking. I forget it.
Your voice
so
is very low.
I will be louder. Is it better
Okay.
now?
Yeah, I can hear you now.
Okay. So actually, my question is about your printing path. You know, because you were showing you can do on-surface printing and you print actually perpendicular to the curve. However, how do you deal in this case with the cantilever problems? Because you know, if you're printing like if you're printing along a curve, you will be having, you know, some layers will cantilever on top of the other one, right?
Yeah.
And also, in my own experience, there is actually quite large problems regarding this cantilever. You cannot extend more than 45 degrees, I guess. So how do you solve this? How can you actually print along the curve without collapsing?
Yeah, I think first we can look at what is the benefit for this we call tangential printing. If we look at vertical printing, and if you are printing, for example, curved element, then you can see every layer you have a little bit overhang, right? So which means you are losing the integrity of structure for this concrete structure. If you are printing in tangential printing, every layer, even you are printing in the curved object, then you have full bond between the layer. So actually, this is the first benefit to have the tangential printing. So to answer your question, how can we print this curved object? It has something to do with the material properties. For example, everything we print is fresh concrete, right? If you add some additive, for example, accelerator or some modifier, then actually you can make it harden faster. You can make the concrete more sticky in this case. So there are some way to overcome, to tweak the concrete material in the fresh state. If you can tweak it, and if you know how to do that, then you can achieve more cantilever in this case. So I don't have one number to answer you like how much degree we can print. It's really based on what material we use, what additive we add in this fresh concrete, then we can have different results.
Thank you very much.
Yeah, welcome.
Yes, thanks, Shaun. I think there's quite a few questions, but I think maybe we can address these questions maybe after your presentation of the script that you're going to show.
I'll unplug this one. Can you still see my screen?
No, not. Just wait a sec. Yes.
Okay, nice. So let me quickly hide this one. And also hide this one. So
Shaun, if you can also move the Teams video, you can also do that too.
Okay. So otherwise, I'll show you this. So if you go to ETH website, and they have a case study, and within the research, there's one blog called buckling simulation for 3D printing in fresh concrete. And it has some description here. And over here, you can download this example file. You open this file, this is what you see. Activate this one. So this is what you see from the beginning. This is a script. And basically, this script is not that long. The left side here, it do some geometry operation. The middle part, it do some current bar assembly. And this is our FEM solver. The last part is just showing some text on the screen. So actually, last part just is not that important. So I will quickly go through some of the process now. I cannot go to too detail. I want to give you some general idea. Spend around maybe 15 minutes. So first, we need to generate the geometry, right? We want to see what kind of geometry we want to test. So over here, let me hide the result first. So over here, we create a cylinder. It's a very simple cylinder with a radius in 0.25 meter. So everything we work in here is in meter. The unit is meter. And this cylinder is with a height 1 meter. And we want to analyze this cylinder using this buckling simulation. So after you create your geometry, you need to do some contour. And this contour is based on the layer height we have. So for example, most of the time we print is 1 centimeter as a layer height. So I choose 0.01 meter in this case. And with this list item, then it can mimic, for example, the green line is the how many layers you are printing now. If I hide this one, if I hide this one, and then disable this one. Then you can see what is the current layer, right? For example, if you want to analyze what happened in layer 30, then you simply to drag this slider to 30. So this is let you to choose the layer count. Now, and I enable this one, and based on that, how to say? Maybe I can go through this one first. Because Karimba can only take mesh, so we need to convert our NURB surface from Grasshopper to mesh. So this is what we do. I disable this one first. And there's another important thing, because when we apply the material properties, every layer has a different material properties. Because when you print the first layer and second layer, first layer is already dry. So first layer, it has higher strength compared to the newly printed layer. And if I show this one, and I click it, this part is to allow you to generate the surface, but separately manner. And of course, you can adjust this U and V count. The more V count you have, then more dense of your structure can have. But I would say the higher V count, you can have more accurate results, but also it takes more computational time. But our case, this is actually not 100. And I hide this one. Second thing is we need to customize our material properties. As I described before, every layer we have a little bit different material properties. And this property actually is based on, go back to the graph, based on these two graphs. So basically these two graphs will tell you what is the initial strength of your concrete. It's a linear line over here, it describes the strength development of this concrete. And based on these two, you can get this one is the function for the Young's module, and this one is the yield strength. So this is the two function I get on the previous two graphs in linear function of time. And based on that, I choose the isotropic to make everything simpler, and then assign to the section element. And over here, you can see the height I give 5 centimeters. So this is the height I basically to mimic our print width. So if you are printing wider, for example, 10 centimeters, then you choose this slider to 10. And this is a shield. Enable this one. And you can see how fast it calculates the FEM. So based on that, the first thing I will do is calculate the length of every layer. So remember the unit we are working on is in meter. So this is the circumference of the curve of every layer, because we are building a cylinder. So every layer, the length is always the same. It's 1.57 meter every layer. Based on that, we convert the length to a millimeter. So we multiply 1000. And if you divide your print path length to our print speed, then you can get the edge of every layer, right? Which means it takes 0.3 minutes to print first layer, then to second layer and third layer, and so on. With this one, we made a very simple Grasshopper script. You can basically to increment this edge for you. So let's look at the result of this script. So what does it tell you? For example, if you print up to layer, let's say 19, the newly printed layer, the edge is 0.3 minutes. And the first layer is already 5.9 minutes. So every layer, it has different edge. Then I can take this edge to the function I just showed you before, to Young's module and also the yield strength. And then you can make use of this Karimba customized material properties, and basically to create the material properties of every layer. So this is the property of the material in every layer. Then this part, it makes some support setting, and it also define the stiffness of the support. So over here, this is the cross section, and basically we take the support as a spring, and we define this translational spring stiffness and this rotational spring stiffness. But to be honest, these two values over here, we how to say, we calibrate because we previously we didn't really know these two values, so we calibrate until our model is matched to the physical experiment. So actually, these two values are made by trying and error. And then the spore we make with fixed translation, also fixed with rotation, and the load is only gravity, so dead load. And then you assemble all the element together using the Brain-Box 3D assemble model. You run this software, FEN software, then you can get a displacement. And over here, basically, it's just to visualize what is the result to you. So if you able to preview, then I disable this line. Let's go to the perspective maybe. And you can see the layer 20, we have maximum displacement with 0.467 centimeter. And from our experience, if maximum displacement is larger than 1 centimeter, which means it will collapse. So if I make it to layer count 30, so it's already like over 1 centimeter. Actually, it aligns with what we see in this geometry. So this is also around layer 30, and also with the experiment we have in Singapore, it's also we can bring up to layer 20. So yeah, this is the general idea, like how you can use this buckling simulation. So yeah, that's it. If you have any question, you can let me know.
Thank you, Shaun, for showing us the script. Yes, there's actually quite a few questions. The first question is actually, someone asked, is it possible to apply the Crumber buckling simulation definition on top of topology optimized shape? I guess this is a question on you, Shaun, or also on Clemens.
Yeah. So I think topology optimization and buckling simulation, they are two different scripts, right? One is to minimize the amount of material you apply to your geometry, and also another one, buckling simulation, is allow you to predict what will happen according to your geometry, material, and your printing speed, and so on. So yeah, of course, it's able to combine. Maybe you can use, for example, Grasshopper or other evolutionary software to get the most optimal results. So yeah, it's possible. There's no problem.
I think also that it could be possible if you take the buckled shape and derive some fictitious stresses from this buckled shape. It should be possible to do this optimization based on these shapes.
Yeah.
It should also make sense, actually.
Yeah, it's absolutely possible, and this is one reason we want to apply topology optimization in concrete printing, because you don't have to customize any formwork. You can just print optimal geometry through concrete printing.
Thank you for that. Inka also asked in relation to this, thank you for the interesting insight into topology optimization. You mentioned an assignment of different properties for tension and compression of the material.
Yeah.
How do you treat the anisotropic material behavior of printed concrete, which occurs due to the layer upon layer technique?
So in this case, in the buckling simulation, we don't tackle that. I basically keep it simple as isotropic material in here. But in the topology optimization, actually, when you apply the load, then you need to treat it differently, right? For example, if you do the pre-stress or post-tensioning for your concrete structure, in the loading scenario, you have live loading, and you have dead load, and you also have the load from post-tensioning. So all these need to be taken into account for topology optimization.
Thank you for that. Andrea asked, hi all, excellent research. Question, what is the concrete strength class used for the columns and walls, and which water cement ratio have you sort of used?
Yeah, okay. So actually the concrete printing material, after 20 minutes, we can get around 20 megapascal. And after say 1 hour, we can get something like 40 megapascal. It's really depend on did you add additive or not for the cement accelerator and so on. So this value actually is quite different according to the material properties. What's the second reason? The second question, sorry.
Second question was the water cement ratio.
So I think water is 16% of the cement. So 60%. But it also depends on what material you use. We use a different material. So sometimes like 20%, sometimes like 16%. It's quite depend who is your material supplier. Yeah.
Then in relation to the material, someone asked, how did you test the properties of the material, like the compressive strength and the Young's modulus in the fresh state?
The fresh state. Okay. So let's go back to the. So this is our testing device in Eindhoven University. Actually, we also have the same one in Singapore. So basically, normally when you want to test hardened concrete, you would take the cube and cylinder, right? And actually, this is also the same for fresh concrete. You also take the fresh concrete you cast and compact it into the cylinder and cube, and you wait there maybe 15 minutes. So the concrete is already a little bit dry. You already have the strength and stiffness to support the self wave. You remove the mold, and then you place your testing sample below here. Once you place below here, then you add the sand in this empty chamber. So your loading scenario is added incrementally, and then you are able to measure what is the weight you are currently loading on the sand, and what is the displacement it occurred on this sand. And the right side is another testing method for the shear. So you apply the force from the different location. So yeah, this is the way we test our fresh concrete.
Then in relation to the sort of testing, experimental testing and stuff like that, Theo asked, how do the experimental values compare to the Karamba predictive values from your experience? I know that you've addressed this aspect in your sort of paper or the writing, but maybe you can elaborate a bit further.
So to validate the result, right? So actually, you can go to Witteveen+Bos, our digital construction website, and the project in the block category, you can find our big bargaining simulation in 3D concrete printing in detail. So how do we validate our bargaining simulation? Let's go to the validation paragraph. This one. So basically, we do two-step. So based on the paper from TU Eindhoven, thank you for their pioneering research works. So we have something to compare. So we use the TU Eindhoven, their research results as a benchmark, and they use the FEA software like the Abacus, and they also do some physical comparison with the printing experiment. So we just use our bargaining simulation to compare their results. And over here, you can see this is the result. The first image is from TU Eindhoven, from Abacus analysis. And you can see over here, this is the result. For example, the red line, layer 32, it has buckling because it has a 4 millimeter in the buckling, buckle in 4 millimeter, but in current bar, actually it buckle 12.7 millimeter. So it actually has 3 times larger than abacus. Then we compare with the physical experiment. In the physical experiment, we can see at layer 29, it has 15 millimeter in displacement. But in current bar, it has 10 millimeter the buckling displacement. So both abacus and current bar, you overestimate the stability of the concrete structure. That is probably because when we do the testing method, you need to collect your fresh concrete, right? And once you collect it, maybe you need to do some compaction to make sure there's no air bubble in your testing sample. And that compaction, it increases the strength and stiffness of your testing sample compared to the printed concrete structure. So if we can calibrate our material testing result, then I think we can also to calibrate our digital buckling simulation result. Yeah.
Thank you for that. So there were a couple of questions, which is a similar topic, which relate to material. I guess someone has already addressed it to you personally, but can the same code be used to print with clay? And for example, how then can one input the properties of our own materials, for example? And this, of course, is possible. Maybe you can elaborate a little bit.
Yeah, I think this is all pretty much depend on what is the performance of Karimba, right? I think Karimba you cannot do clay, but of course in the general idea is quite the same. I know clay printing and concrete printing is in principle is quite similar, but clay is way lighter and also is more sticky. So in terms of buildability or what to say, it's easier to print compared to concrete. So you cannot directly to take this script to clay printing. You must align your material property first from concrete to clay. Then maybe you can play with this buckling simulation in clay printing. But I have never tried, but I think FEM basically is it should be possible in my opinion.
Yes, basically, I think you have input the materials properties. So this is something that maybe also Clemens can also address, like in terms of material properties in Karamba.
I mean, you can set the Young's modulus, the ratio of lateral expansion, so the shear modulus. So, and of course the specific weight. So it would be definitely possible to adapt the material properties in such a way that you get realistic results out of the calculation.
Yeah. Stop sharing.
But it's a matter of getting the right parameters in place.
Yeah.
I would say.
First, you need to get the correct material properties. Then you can make use of the FEM. Either you use abacus or Karimba. But first, you need to have the understanding of your material.
Yeah, we actually have quite a lot more questions because we have around 5 minutes left. So I would maybe just ask one or two last questions. These are relating now to the presentation that you had, for example, in terms of robots. How do you solve the additional 7th axis if the robot is mounted on the linear axis?
Yeah, so yeah, how to say, this is the, I don't want to say this is the magic of our robot controller, but basically you need to give the extra information for robot, right? If you want to move your entire robot to the certain coordinate, for example, you can give extra X, Y, Z linear coordinate to robots. So when you have 6 axis robotic arm that doing its own job, then you just simply to give the extra coordinate, for example, X or Y or Z coordinate, then your linear track will move to this specific location. That's it. There's no, yeah, it's quite easy.
And maybe one other question is, Mitchell asks, can you explain the difference in obtained results between Abacus and Karamba. Is this something that you are? I think you explained it a little bit.
I'll explain this question. So both Abacus and Karamba, they overestimate the stability of our fresh concrete structure, and they should be calibrated. This difference probably because we do some compaction for the fresh concrete testing method. So if we can calibrate our material properties on the fresh concrete, then it should align with the vertical. Sorry, it should be aligned with the physical experiment.
And maybe we'll leave all the other questions because there are quite a few questions for you, Shaun. I think there's a lot people who are interested in this topic in general.
Yeah.
Thank you once again for sharing the work and the research that you're doing over there in Singapore and in the Netherlands.
Yeah.
If people wanted to sort of get in touch with you, of course, I'm just putting a last slide, for example, where people can.
Yeah.
I have your email there address. I guess they can contact you personally with some of these questions that they've posed.
Yeah, of course.
I hope that's okay.
Yeah, it's okay. It's okay. You can just send me an email, and if you want to see some beautiful concrete structure, just email me, and we can do design, engineering, and print this beautiful concrete structure to you. So please let me know.
Yes, and thank you very much once again for joining us, Shaun.
Yeah.
Thank you for your time, and thank you for everyone else, like the attendees, for watching today. I hope today was a very different presentation from us. This is the first time we've done this sort of presentation style, so we're hoping that it worked out for everyone. For those who maybe have missed the webinar or who came in late, we will be posting this on our webpage afterwards so that you can also access it. And like we said, feel free to contact Shaun if you have any specific questions relating to these topics.
Yeah.
Or you can also contact us as well.
Yeah. And if you have your own customized concrete material, you can just let me know. We can also test it out for you for this buckling simulation. There's no problem.
And basically, one of the ideas of releasing the script, is so that we can sort of collaborate and share with the wider community in this sort of research topic too.
Yeah, it's an open source, so you are more than welcome to download.
Yes. So thank you once again to everyone.
Yeah.
So from us here at Karamba, and then to you, Shaun, and then to all the attendees.
Yeah. Thank you, everyone.
We hope to see you next time for another webinar.
Thank you. Bye-bye.
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 Bye.